Hi, welcome back to my class in Advanced Statistics. For today, we will take up the second of the three important probability distributions. We are we are almost done with the first one, the binomial probability distribution. For today, we will take up the Poisson probability distribution. But before that, we take the mean and standard deviation for a binomial random variable. The mean for a binomial random variable is denoted by the Greek letter mu and is equal to the product of the number of trials n and the probability of success. You recall that in binomial experiment there are always two possible outcomes for each trial, and the probability of success for each trial is denoted by P, and the number of trials is denoted by small letter n. And the product of n and P is the mean of the binomial random variable. The Greek letter mu denotes the mean of a binomial random variable and is equal to the product of n, the number of trials in binomial experiment, and the probability of success. And this mean of for a binomial random variable is actually equal to the expected value of x, which we have taken before, the expected value of x. Now the standard deviation is the square root of the variance for a binomial random variable. And the variance for a binomial random variable is denoted by the square of the Greek letter sigma. This is the Greek letter sigma, and sigma squared denotes the variance or variance for a binomial random variable and is equal to the number of trials multiplied by the probability of success multiplied by the probability of failure. Now, the probability of failure Q is the complement of the probability of success. That is the sum of the probability of success P and the probability of failure Q is equal to 1. And from that equation, if you know the probability of success P, then the probability of failure Q is equal to 1 minus the probability of success P. And if you take the square root of both sides, the square root of sigma square is sigma. And the square root of the right hand side is equal to the square root of n multiplied by p multiplied by q. And this is the standard deviation for a binomial random variable denoted by sigma is equal to the square root or the positive root or the principal root of the product n multiplied by p multiplied by q. Now we take an example for applying the mean and standard deviation for a binomial random variable. Consider the following problem. A manufacturer believes that 30% of all consumers favor his product. To check his belief, he randomly samples 800 consumers and counts the number X favoring his product. If 30% of all consumers favored the manufacturer's product, within what limits would you expect X to fall? In this example, the variable X represents the binomial random variable. It is a binomial random variable because in this problem, each consumer will be asked if he or she favors a product of the manufacturer or not. Hence, there are only two possible outcomes in this problem. Either the consumer favors the product of the manufacturer or the consumer does not favor the product of the manufacturer. And it is given that 30% of all consumers favor the manufacturer's product. And from this population of all consumers, a sample of 800 consumers were taken, and X would be the number of consumers from 800 who favored the manufacturer's product. And 30% of 800 is 240. And this is a binomial experiment because the trials are independent, which means that the decision of one consumer to favor the manufacturer's product and the decision of the next consumer who may or may not favor the manufacturer's product are completely independent. And each trial may be repeated n times, and for this example it will be repeated 800 times because there are 800 consumers and each will be asked whether he or she favors or not the manufacturer's product. And the probability that a consumer favors the manufacturer's product is 30% or 0.30. And the sample size is denoted by small letter n, and it's equal to 800. And we are asked to find the limits where we would expect the value of x to fall. And in this particular problem, we use the Chebyshev's theorem and the empirical rule. According to Chebyshev's theorem, 68% of the sample of 800 consumers, approximately 68%, by Chebyshev's theorem, 3/4 or 75% of the sample fall within 2 standard deviations from the mean. That means we have to compute the mean for this example. And according to empirical rule, 68% of the sample of 800 consumers would favor. There are 68% of the sample of 800 consumers that fall within 2 standard deviations from the mean. Moreover, according to Chebyshev's theorem, we almost 8/9, or that's 88.89% of the sample of 800 consumers would favor the manufacturer's product, and they would fall within 3 standard deviations from the mean. And to calculate these limits, we need to find first the mean and the standard deviation for this example, where the mean is denoted by mu and is equal to n multiplied by p, where n is 800 and p is 0.3. On the average, we would expect the number of consumers from 800 who favor the manufacturer's product to be 240 consumers on the average. And we also compute the standard deviation. It is the principal root of the product of n multiplied by p multiplied by q. As I said earlier, Q is the probability of failure. In this example, PQ is the probability that a consumer does not favor the manufacturer's product. And it is the complement of P, the probability of success. If Q is the complement of P, then Q is equal to 1 minus P, where P is 0.3, and 1 minus 0.3 is 0.7. So we multiply 800 by 0.3 by 0.7, and we take the root. And we compute this value using our calculator. We have the square root of 800 times 0.3 times 0.7. And to 2 decimal places, you should get 10.88. Now we would now compute or find the interval or the limits that contains 68% by empirical rule or 75% by Chebyshev theorems, the interval that contains 68% or 75% of the number of consumers who favor the manufacturer's product, and we would also compute the interval with the lower and upper limits that contain 8 over 9 or 88.89% or by Chebyshev's theorem or almost 100% by empirical rule that contains 8 over 9 by Chebyshev theorem of 800 consumers who favor the manufacturer's product, or almost 100% of the 800 consumers who favor the manufacturer's product that fall within 3 standard deviations from the mean. We now compute the interval that contains the number of consumers from 800, sample of 800 consumers who favored manufacturer's product and that are within 2 standard deviations from the mean. And this is the interval that contains the number of consumers who favor the manufacturer's product that are within 2 standard deviations from the mean. And the lower limit of this interval is mu minus 2 sigma, and the upper limit is mu plus 2 sigma, where mu is the mean of the binomial random variable, which we have computed earlier, is equal to 240. That means on the average, we expect to get 240 from 800 consumers who favor the manufacturer's product with the standard deviation denoted by sigma equal to 10.88 as we have computed earlier. And we substitute mu and sigma into these lower and upper limits. Mu is 240 minus 2 times sigma is 10.88. The upper limit is mu 240 plus 2 multiplied by standard deviation or sigma 10.88. And using your calculator, you compute 240 minus 2 times 10.88, and you should get 218.24. And this is the lower limit of the interval, of this interval. We compute the upper limit using our calculator. We have 240 plus 2 multiplied by 10.88. And you should get 261.76. Hence, the number of consumers who favor the manufacturer's product from the sample of 800 consumers, we expect that number to fall between 218.24 and 261.76. And the probability that the number of consumers from 800 who favor the manufacturer's product will fall within this interval or within these lower and upper limits has a probability of 75% or 0.75 or 3/4 by Chebyshev's theorem, or with a probability of 68% or 0.68 by empirical rule. Again, by Chebyshev's theorem, the probability that the number of consumers from 800, from the sample of 800 who favors the manufacturer's product would fall between 218.24 and 261.76 is 3/4 or 75%. And by empirical rule, the probability that the number of consumers from the sample of 800 who favors the manufacturer's product would fall between 218.24 and 261.76 is 68% by empirical rule. Now we would compute the limits within which the number of consumers who favor the manufacturer's product from the sample of 800 consumers are within 3 standard deviations from the mean. We now find the interval within which the number of consumers from the sample of 800 consumers favor the manufacturer's product lie within 3 standard deviations from the mean. And the lower limit and upper limit of this interval are given by mu minus 3 sigma for the lower limit, and the upper limit is given by mu plus 3 sigma, where mu and sigma, as we have shown earlier, are equal to 240 and 10.88 respectively. We substitute these values of mu and sigma to find the lower and upper limits of the interval that contains the number of consumers from 800 consumers who favor the manufacturer's product and that are within 3 standard deviations from the mean. Substituting the value of mu, 240 minus 3 times sigma is 10.88 is the lower limit. The upper limit is mu, 240 plus 3 multiplied by sigma, 10.88. And we compute this lower limit and upper limit using our calculator. We start with the lower limit, 240 minus 3 multiplied by 10.88. And you should get 207.36. And we compute the upper limit using our calculator. We have 240 plus 3 multiplied by 10.88. And you should get 272.64. Hence, from the sample of 800 consumers, the number of consumers who favor the manufacturer's product would lie between 207.36 and 272.64 with a probability of 8 over 9 or 88.89% by Chebyshev-Churan. By empirical rule, the probability that the number of consumers from 800 consumers who favor the manufacturer's product would lie between 207.36 and 272.64 is almost 100%. That is, from the sample of 800, the number of consumers who favor the manufacturer's product would lie between these numbers has a probability of almost 100% by empirical rule. Again, this is the interpretation of the result we obtained from the sample of 800 consumers. The number of consumers who favor the manufacturer's product would fall between 207.36 and 272.64, has a probability of 3/4 or 75% by Chebyshev theorem, and with the probability of almost 100% by empirical rule. And that completes our example. Now we will define and describe the Poisson probability distribution. The second of the three important probability distributions is the Poisson probability distribution, and the other two being the binomial probability distribution and the hypergeometric probability distribution. The Poisson probability distribution is useful for data that represent the number of occurrences of a specified or a specific event in a given time period or space. Examples of variables for which the Poisson probability distribution is useful are as follows. The number of tourists who approach the immigration officer in NAIA during a given 3-hour period. Another example would be the discrete random variable representing the number of complaints received by customer service personnel of PLDT during a given day, during the Typhoon Ulysses. And another example would be the number of customers who fall in line to pay for the groceries they bought from a supermarket. And now we define and describe the probability of the discrete random variable x, representing the number of occurrences of a specified or specific event during a given time period or space. Let x be a discrete random variable representing the number of occurrences of a specified event in a given time or space. Let mu equals expected value of x. So mu here is the average or the mean of the values of the discrete random variable x, or it is the expected value of x. Then the probability of the discrete random variable x, representing the number of occurrences of a specified event in a given time period or space, is given by the following formula. Probability of x is equal to mu, the expected value of x, raised to the power x, multiplied by e to the minus mu, divided by x factorial, where the values of x would go from 0 to positive infinity. And this is one of the differences between the Poisson and the binomial probability distributions. In Poisson probability distribution, the values of the discrete random variable x goes from 0 to positive infinity, while the values of a discrete random variable for a binomial probability distribution, or the values of binomial random variable, are finite. That is, it begins from 1 and it ends to a specific or specified number, depending on the sample or number of trials. And mu, as I said, is the expected value of x, which means it is the average number of values of the discrete random variable x. And e is, as you have learned from your plane trigonometry, it is the base of the natural logarithm. And e is equal to this decimal number, 2.718281. And e is actually a non-terminating, non-repeating decimal number, which means that e is an irrational real number. And in the denominator, we have x factorial. When x is 0, we define 0 factorial as 1. We now take an example for applying this formula to calculate the probability of a specific value of discrete random variable x. For our example, consider the following problem. Meralco reports that power outages occur randomly and independently of one another at the rate of 4.2 per year. The probability distribution of x, the number of power outages occurring during a given period of time, is described by the Poisson probability distribution. Find the probability that letter A, no power outages occur during a given 4-month period. Letter B, no more than 2 power outages occur in a year. First, we write the given information in the problem. We start with 4.2 per year. That is the expected value of the discrete random variable x, representing the number of power outages in a given period of time. And in 1 year, the average number of power outages reported by Meralco is 4.2. And in letter A, we are asked to find the probability that no power outages occur in a given 4-month period. Since the average number of power outages is given in a period of 1 year, we have to convert the 4-month period into year. And we know that in 1 year, there are 12 months. And we convert 4 months into year by multiplying 4 months by a conversion period. The conversion period is a fraction where the denominator is 12 months, so that the months in the numerator and the months in the denominator will cancel out. And in the numerator, we write 12 months is equal to 1 year. And months will cancel out, and we reduce 4 over 12 to the lowest terms, that is equal to 1/3. One-third year. Hence, this 4-month period is equivalent to 1/3 year period. And in letter A, we want to find the probability that no power outages occur in a 4-month period or 1/3 year period. And if there is no power outages in this given period, then the value of x is 0. And we want to find the probability that x is 0. That is, no power outages occur in a given 4-month period or 1/3 year. And we will use the formula for calculating the probability of the value of the discrete random variable x, described by Poisson probability distribution. Calculate the probability of no power outages in a 4-month period or 1/3 year period. We use the formula for the probability of discrete random variable x, described by Poisson probability distribution. P of x equals mu to the power x times e to the negative mu divided by x factorial, where mu given in the problem is 4.2 power outages in a year. But in letter A, we want the probability of no power outages in a 4-month period or 1/3 year. Hence, to get the average number of power outages in a 4-month period or 1/3 year, we divide this average number of power outages in a year by 3. Or we multiply 4.2 power outages in a year by 1/3. Because 4-month period or 4 months is equal to 1/3 year. And using our calculator, we divide 4.2 by 3 and we round it off to 2 decimal places. We have 4.2 divided by 3 is 1.4. The average number of power outages in a year is 4.2 power outages. For a 4-month period, the average number of power outages is 1.4. Obtained by multiplying the power outages in a year by 1/3 because 1/3 year is equal to 4 months. Or 4-month period is equal to 1/3 year. Now we calculate the probability that there is no power outages in a 4-month period. We have mu is 1.4 for 4-month period. To the power x, x is 0 for letter A. Multiply by e to the power negative mu. Mu is 1.4 for 4-month period. And divide by x factorial where x is 0. And we know from algebra that 1.4 to the power 0 is 1. And 0 factorial, as we said earlier, is defined as 1. Therefore, in our calculator, we only need to compute e to the negative 1.4. We have e to the power negative 1.4. And the answer in your calculator, you multiply that by 100 and then you round it off to 2 decimal places and the answer should be in percentage. And you should get 24.66%. Hence, in a given 4-month period, the probability that there will be no power outages is 24.66%. In letter B, we are asked to find the number of outages. The probability that the number of outages is no more than 2 power outages in a year. If no more than 2 power outages in a year is required, then 2 is the maximum number of power outages in a year. And the values of x for the number of power outages in a year is less than or equal to 2. The number of power outages is no more than 2. That means the values of x, the number of power outages in a year, should be less than or equal to 2. And we want the probability that x is less than or equal to 2, or the number of power outages is no more than 2 power outages. It can be 2 or less than 2. And the values of x that are less than or equal to 2 are 0, 1, and 2. Hence, the probability that x is less than equal to 2 is equal to probability of x equals 0, no power outages in a year, plus plus the probability of x equals 1 power outage in a year, and plus the probability of x equals 2, 2 power outages in a year. Because in letter B, we are asked to find the probability that no more than 2 power outages occur in a year for the value of the average mu, or the expected number of power outages in a year, we use mu equals 4.2. And the probability of x equals 0 equals mu 4.2 to the power 0. Multiply by e to the negative 4.2. Divide by x. For the first term in this sum, x is 0. 0 factorial. Plus the probability x is 1. Mu is 4.2 to the power x is 1. Multiply by e to the negative mu. And mu is 4.2. Divide by x factorial. For the second term in this sum, x is 1. Denominator is 1 factorial. Plus the probability of x is 2. We have mu is 4.2 to the power 2. Multiply by e raised to negative mu 4.2. Divide by x factorial. For the last term in this sum, x equals 2. Hence denominator is 2 factorial. For the first term, 4.2 raised to 0 is 1. 0 factorial is 1. Hence, we only need to compute e to the negative 4.2 for the first term. We have e to the negative 4.2. And the answer in your calculator is a decimal number. Multiply that by 100 and round it off to 2 decimal places. And then you write the percent sign. And you should get 1.50%. Hence, the probability that there will be no power outages in the year is 1.50%. Plus the second term, we compute this in our calculator. 1 factorial is 1. We have 4.2 raised to 1 multiplied by e to the negative 4.2. We have 4.2 multiplied by e to the negative 4.2. And the answer in your calculator is a decimal number. Multiply that by 100 and write the percent sign. And multiply this decimal number by 100 and you round it off to 2 decimal places. And you should get 6.30%, 6.30%. Plus the last term, we have 4.2 multiplied by 4.2 squared multiplied by e to the negative 4.2. 4.2 squared multiplied by e to the negative 4.2. And divide by 2 factorial. And 2 factorial is 2. And the answer in your calculator is a decimal number. Multiply that again by 100 and you write the percent sign. And you should get 13.23%. And add these three terms. 13.23 plus 6.3 plus 1.5, and you should get 21.03%. Hence, the probability that the number of power outages in a given year is no more than 2 power outages is 21.03. If you are asked to find the probability that there will be more than 2 power outages in a year, that is x is 3, x is 4, x is 5, etc., then you simply subtract 21.03 from 100, and that's the probability that the number of power outages in a given year is more than 2 power outages. And this completes the solution for our example. For your practice, please try the following exercise. The number of people X entering the intensive care unit at a local hospital on any one day has a Poisson probability distribution with a mean of mu equals 5 persons per day. Find the probability that the number of people entering the intensive care unit on any particular day is A, 2 people, B, greater than 5 people. And that completes our lesson for today. We will continue next time with the mean and standard deviation for the discrete random variable described by Poisson probability distribution. If you have question about the lesson today, you ask your question in the comments below. And don't forget to subscribe to my YouTube channel, Art Calison, the channel of learning and leisure. Thank you for joining me in my class today in Advanced Statistics.